iodine, it means that there is a progressive increase of blood-brain barrier breakdown to different molecules. Then we confirmed our observation using electron microscopy, and here you can see that lanthanum, this is found in the basal lamina. This is one endothelial cells. And the most interesting point is that one endothelial cell is completely infiltrated with lanthanum, but the adjacent cells were not. So it means that this is a very specific phenomena going on particular endothelial cells. This is not all or none phenomena. This is another example of microvessel from the spinal cord. You can see edema is here, swelling. But you see the tight junctions, that is the constituent of blood-brain barrier, they are not broken down. We can see some vesicles, microvesicles transporting lanthanum from the endothelial side to the cellular side. And on this vesicular transport, yesterday, 3 people from the United States of America were awarded Nobel Prize of Physiology and Medicine for this year. Then the question is, whenever we have breakdown of the barrier, can we have edema? The answer is yes. And here we have measured water content in different segments of the spinal cord, and as early as 5 minutes after, we can see increase in water content in particular segments that are very near to the injury site. But over the time period, almost all segments got some edema, so this is a progressive period up to 12 hours. When coming to the cellular changes, you can see that this aspect, the T9, all changes were not measured in the area that were lesioned. This is from rostral side, you can see. And these are neuronal damage, cell death, and sponginess as compared to the control group. I told you that glial cells, they are almost much more in number. What they are doing, it's not the question of only neurons. I have shown endothelial cells. You can see here, there were great differences from the right side, means the injury side in T9, and this is the T9 left. So ipsilateral and contralateral showed although equal response of GFAP, but the injured side having much more. And another question is that when we have given a drug, they were given before, like naloxone and endomethacin, the glial activation was not much there. Myelin basic protein is another part that is very important for a spinal cord injury, for our movement and many other things. You can see that this is T12 right side. Degradation of myelin in terms of this is normal. The redness is much less there, and many tracts and fibers cannot be seen here. At that time, people believed that pathology means long time, weeks, months, or years. But we never believed that pathology can take so long time. So we have shown that even in 5 hours, there is upregulation of CFOS in T9 right side and also in ventral horn. It means whatever the injury signals are coming from the T10 level, they are really making cellular changes. And the final proof of the concept that what we see, we believe. And this is an example of electron microscopy. You can see probably one activated microglia. There were so many holes, or we can see edematous swelling in terms of electron microscopy. This is on the right side. The left side is much less, although the changes were much more prominent. The same thing happens to the myelin vesiculation. These myelin on the right side were much more damaged as compared to the left side. So there are side differences prevail. Obviously, we cannot go for pinpointing one particular chemical or one particular substance. So you can see that we have just listed, this list is not complete. There are many endogenous neurodestructive elements are released after trauma or injury, and there are simultaneously so many neuroprotective factors are also released. We have just given some summary, and therefore we have given some example of BDNF, that is brain-derived neurotrophic factor. Topically, it is protecting as compared to these normal circumstances, untreated. But when we have given a combination, not only from brain-derived neurotrophic factor, but also glia-derived neurotrophic factors, the combination is much more important in neuroprotecting the spinal cord after injury. So it means we need many things at one time that can have better neuroprotective approaches. I skipped because we have no time. These are the point that also the radioiodine extravasation was also reduced by BDNF if given -30 to +10 minutes time. But after 30 minutes or 60 minutes, the effects were not so pronounced. This is one of the examples of crosstalk in central nervous system. When you have given brain-derived neurotrophic factor or glia-derived neurotrophic factor, they are not working directly on nitric oxide system. But here you can see that they were able to reduce the upregulation of neuronal nitric oxide synthase after BDNF or IGF-1 treatment. It means that in system or in vivo, the crosstalk can also occur. And obviously we have tested at electron microscopy, BDNF treatment really reduced lanthanum extravasation after the injury. The same thing also happens with another hemoxygenase type 2. They were also reduced and increased at the time of injury. This is just showing you a combination of brain-derived neurotrophic factor, glia-derived neurotrophic factor, and ciliary-derived neurotrophic factor was most effective after a spinal cord injury. But now I am coming to the nanoparticles. I show you this example that if we are going on right path, these are the human spinal cord after 6 hours of motor vehicle accident collected from University of Perth. Byron Kakulus is one of the leading neuropathologists in the world, and you can see this leakage of albumin is typically shown in human cases of a spinal cord after 6-hour injury. But the philosophical point is that we have no idea that the 6 hours in human life, how we can equate with 6 hours in rat life when the rat life is 2 years and human can survive for 70 years. But these are the questions. It's the 6 hours after the leakage of albumin. So we believe finally that, of course, if we are going to reduce this blood-CNS barrier permeability, we are going to have neuroprotection. And finally, this is the drug called cerebrolizin, and it comes in ample form, and we have a couple of publications on cerebrolizin. The doses are 2.5 to 5 milliliter per kilogram. It has clinical trial in Alzheimer's disease in the United States. It is approved by US FDA, and also a stroke, and nowadays it is they are trying for Parkinson and other diseases. We have some presentation in 6th clinical trial of Alzheimer's disease in San Diego in November. So this is a very powerful drug. And then we have labeled with titanium nanowire by Dr. Wang. We have used 20 to 30 nanometer titanium nanowires. And I skip this brain injury part because I have no time. I can tell you here that when we cannot compare also the exposure of silica to a human and exposure of silica to rat, but we got some data based on many other physicochemical factors. So we have given silica dioxide 40 to 60 nanometer in size for 1 week in rats, and after that we made the injury, and this is one of the master thesis done by one of my students at Uppsala University, and this is also spinal cord injury and leakage of albumin in different conditions. I want to show you these are the damages, and these damages can be exaggerated by if they are exposed to nanoparticles before. But look here, spinal cord injury 5 hours when they were intoxicated with silver nanoparticles, and cerebrolizin was given alone. We have some result, but not better. But when we have given nanowire cerebrolizin, this is much more better whether they will receive silver or copper nanoparticles before the injury. And these are some examples. The silica treated spinal cord is much more damaged here, and you can see that the cell loss here is much more higher in silica treated as compared to the saline, and also the barrier and edema were much more higher. So the point is that if nanoparticles were intoxicated before they are in the system, might be they are producing much more higher oxidative stress, and therefore the identical injury can exacerbate the pathophysiology. So here we have done titanium nanowires, and the point is that we have chosen 3 different kinds of drugs, not cerebralizing here. The question is that, I will finish in 5 minutes. The question is that, if we nanowire any drug, A, B, C, can all nanowires, just by nanowiring, all drugs could be good, become good? Or still, nanowiring can only enhance the capability of certain drug if some drug is producing 100%, 80% or 30%. This was tested here. And also the time. If we nanowire, this is not a panacea. So we have to study the time relation. And this was shown here in one example, that this is untreated. If we have given nanowire drug 5 minutes after, it is much more better. 1 hour after, less effect. And this is in different segments. The same thing happened also with blood-brain barrier. 5 minutes after given is much more better than after 1 hour. This is the same thing. Now the question is that, we have different drugs. Let us say, I cannot disclose the real name, so let us go SCI2 at different time, 5 minutes and 5 minute and combination. You can see that if we have given one time, they are better in motor scale up to 3 hours. When we have given in second dose, they can do better. But if they are continued, the other drugs, they are not doing that good. So it means that different drugs, the nanowiring can only enhance the effect of the drug. It cannot change a bad drug to good drug. And this is also seen here. The one drug that was very good is good, and the other drugs were not very effective. This is untreated line. So here, the statistical analysis were given, and there are 4 compartments. You should look here. This is the worst. This is the worst compartment, untreated or spinal cord injury. Here there are different areas, laminectomy, and different drugs were given. Some of the drugs were lying in between, but some of the drugs are in this compartment. So my point is that nanowire drug is not able to enhance or convert a bad drug to good drug. Still, the differences will prevail. And this is an example here that a good drug given after nanowire, it has produced much more better effect than the untreated group. And another example here that also you can see cerebrolizin and indomethacin. Cerebrolizin, when given by nanowire, we have the best result here as compared to indomethacin after spinal cord injury. So only 2 slides are there. What could be the mechanism? Here we have studied the mechanism, and we believe that cellular or molecular stress is very important. We have studied heat shock protein here, and untreated, and after cerebrolizin treatment, we can see that the upregulation of heat shock protein is not very high. It means that whatever we do, it has reduced the level of stress at the cellular level and probably at the molecular level. And this is just an example that some of the work were awarded by Anthony Marmarao. He's recently died, and some of you might be knowing. He's a great neurosurgeon from the United States, and he devoted all his life in studying blood-brain barrier and brain edema. And of course, these works require lots of money. So our former Prime Minister Göran Persson of Sweden is supporting this work, and Sweden is very high in research, and we are very grateful to him. And of course, lots of organizations support this research. I will not read many collaborators from all over the world, and I will stop here, and I look forward to your questions and comments, or any question you have. I would like to try to answer your questions. Thank you very much.
So I have a question on your Tarlov graph.
Yeah.
There was one intervention that had a sudden increased performance.
Yes.
And then dropped again.
Yes.
And why do you propose that profile in sudden recovery and then the recovery disappeared?
Maybe that drug was very short lasting. That could be the reason. We are still analyzing, but we got with that particular drug this effect, and after that it disappeared suddenly. When we have done some combination, it did not change the pattern.
So the nanowire delivery, is that a continuous infusion, or is that?
One time.
One time, okay, that's like a single bolus. So
yeah.
when you see an improvement like that, wouldn't you want to develop a continuous delivery system to try and keep the preserve function
Yes, of course.
persistent?
That we are doing now, because they were done 5 years ago. At that time, nothing was known. So it was just an experiment that we can show. And the other data are already in pipeline, but before we publish or we get approved, I cannot disclose the data.
Well, I'm going to let you call the questions.
Sure.
So,
Yes,
any
please.
other questions?
So very interesting. You talk about nanoparticle can cause toxicity and affect the injury process. Then meanwhile, you also talk about nanoparticle can be used for delivery drugs. So in general, what's your comment about to use nanoparticle to deliver drugs? That is safe way, right way.
That's the question I'm expecting every time, and that's the thing I want to ignite your brain for that. So, as you might have noticed, we have used nanoparticles that are dangerous. In our body, there are so many things that are dangerous. Some are good. So, I think the nanoparticle story is also very same. We have not done on copper nanowire. We have not done on aluminum nanowire. We have at the time used titanium nanowire, because titanium is the most innocuous nanoparticle at the moment that we know. Of course, it depends on dose and time periods. So, to our knowledge, titanium and gold, these two nanoparticles are quite innocuous. We can use this gold nanowire, titanium nanowire. So, since our friend has a titanium nanowire patent, we are trying this titanium nanowire, and we have infused titanium nanowire intravenously for 1 week. We did not get any toxicity in the animal. This research was also supported by a German group. They published in a paper 3 years ago. They have injected in mice intraperitoneally titanium nanowire 200 milligram per kilogram. It's a very high dose actually. And they observed for 5 to 7 days. They do not see any cardiac toxicity or brain toxicity. So therefore we are working on that. We are also working on some other innocuous nanowire delivering the drug. But I cannot tell you, but titanium nanowire is the most innocuous. The nanowires, the nanoparticles that producing damage is copper and silver. They are the most damaging nanoparticles. If we use aluminum in the same size, they are less toxic than copper and silver in the same size and same dose. We are using at the moment 50 to 60 nanometer size of copper nanoparticles, silver and aluminum. So aluminum is the least, copper and silver are much more better if we in toxicity. If we compare copper and silver, I think silver is the top producing neurotoxicity. So there are two ways, even also carbon. So when we deliver the drug, we use innocuous nanowire. So far we have done titanium nanowire. But when we try to study nanoparticle toxicity, we have carbon, magnesium, copper, silver, all these things. They produce toxicity depending on the time, and some of them could be very quick, to 4 hours and 24 hours. Is that answer your question?
Yeah, can I ask one more
Yes.
question? So after nanoparticle is delivered to body, how the body get rid of them? Will this go to urine or go to other
This
places?
is also a very good question, and so far we believe that if we inject copper nanoparticles, and if they are entered into the cell, they can live there for years. There is no way they can get rid from the body. So therefore, and sometimes that can be the possibility to develop cancer. And that's why carbon nanoparticles, there are certain other researchers have shown, if you inhale, they can go to the brain, and then they can come into the circulation. When they come into the circulation, they are free to go anywhere and they can stuck. And that's why this work on carbon nanoparticles, lung toxicity, they can also instill in the lung, and they can produce toxicity. So we believe that titanium oxide nanowires can also go to stuck. But our experiments are only up to 1 week. And up to 1 week, we do not see any toxicity. So we believe that even these nanowires do not come out from the body. They are somewhere in the body, they stick to that. At least in this time period, they have no toxicity.
Thank you.
Any other questions or comments? Tell your mind, there's no hesitation. Whatever you like to tell, please tell.
Okay, thank you very much, Dr. Sharma, for a very provocative talk.
Thank you very much for the opportunity.